All right, and we are back. Cal 1, Summer 2, 2025. So I left on the last video promising that we would get straight into how do we evaluate limits if we're just looking at the equation, right? Or if we're just dealing with, basically from an equation standpoint rather than from what do you call it, just from looking at a graph or even like using a table. However, I was looking over some of the homework and I realized I forgot a couple topics on that first video. So we'll start with those and then we'll get exactly back to that. But the topics that we forgot. So actually, well, yeah, let's do it this way. So let me bring up the book again. All right, so we ended off talking about whether a function was continuous, and what do you call it? Again, we were using graphs, but just looking at these graphs and figuring out whether the function was continuous over a whole window, basically, right? So we call it an interval, but it's basically what we're saying is over a whole window. And usually what we'd see is if it wasn't continuous, then there was one specific point. Usually it doesn't necessarily have to be one point, but you need at least one point where the conditions for continuity aren't met, or certain things aren't met. So again, to be continuous, we need the limit to exist at a point. We need the y value to exist at a point. So we need a point there. We need those two values, the y values there, to agree, right? So be continuous, that needs to be true across the whole window, right? And so when we looked at a couple examples that weren't continuous and there was some different points or different parts of that window where one or more of those three conditions weren't met, right? And so we say it was. So I want to talk about something. We want to talk about something then, taking that idea forward or kind of part of that idea. So there was again these functions that were continuous, and they had different looks to them. They were different functions. In some way or another, they violated one of those three things we need for continuity. So again, we need the limit to exist, we need the point to exist, and we need the y values there for the limit and the point to agree. What do you call it? So there are particular types of, so the places where a function is not continuous, we call it a discontinuity. And there are two particular types. It doesn't mean that this is all the types of discontinuities, but there are two particular types of discontinuities, or two ideas we want to talk out of that. And so one is called, and also, give me a second, let me just make sure the visual on this looks fine. Yeah, actually good. All right. So there are removable discontinuities. There are non-removable discontinuities. I hate worrying about a lot of vowels, because like every time I write that, I'm just like, wait, seriously, is there really this many vowels? There's this many O's and I's in this word? Just seems like crazy unnecessary redundancy. So, removal of discontinuities and non-removable discontinuities. And so again, I'm not saying that all discontinuities even fit these two situations. However, a lot of discontinuities can be classified as either removable or non-removable. And so let's talk about kind of what that means. Well, not just talk about it. So I want to get you guys to kind of guess what that means. So thinking about the word remove, which is what this is all based on. What do you think they mean? Okay, so good. I mean, remove means to take something away. So if I have a removable discontinuity, what they're trying to get at is a discontinuity where I could take it away, or somehow I could make it not discontinuous, or doing the double negative there, I can make it continuous. So there's something I could do to sort of make it continuous. Whereas non-removable discontinuity would be a discontinuity I can't remove. There's no way that I could just sub a point in there. So the idea with removable discontinuities is actually, again, no matter what function you're looking at that has that removable discontinuity, and what of those three properties of continuity or definitions of three things you need for continuity, like what's causing it to not be continuous. The idea is basically you can sub a point in. If you sub that point in, suddenly it's continuous because your limit exists, your y value exists, and those two match. So the idea of removable discontinuity is some sort of discontinuity that you would see on the graph, or that you'd have in the function, where you could sub a point in that just makes it work, basically, that makes that discontinuity go away. Whereas with non-removable discontinuities, or there's discontinuities we're gonna look at where it doesn't matter, like there's no way to sub something in. It is gonna be forever discontinuous. There's gonna be one of those three pieces of continuity that you're never gonna be able to make go away or scrub away. Maybe we could have done this. Maybe we could have done this in different order. That's okay. Let me check something. Let me see if we find something here that has a picture first. Mm. Mm. Great. So I think to start talking about this idea, I want to actually look at something. So this is, I think, section 2.4. We're going to look at all three, at least three or four of these examples out of this section. And just kind of, I want to use this. We're not going to do the exercises. I want to use this just to sort of give you some examples of these discontinuities. So again, this actually, the one good thing about this starts right where we left off. So we left off looking at graphs, trying to identify whether they're continuous or not. So let's start there. 33. So looking at this, is this, in that window, is this a continuous function? Yes. Good. Definitely not continuous. So the next question is, where is it not continuous? Where is it discontinuous? Take a look at that picture, size in, and do whatever you need to do. And I can cheat. Damn. It's not working like it's supposed to. Good. So looking at the picture, notice that right here at -2 and right here at +2, that x equals -2 and x equals +2, we have a discontinuity. Yeah, so it's not at -2, the limit from the left is positive infinity, and the limit from the right is negative infinity, so that doesn't even have a limit there. And the same actually at +2, just reverse order. But there is no limit of either of these, therefore can't be continuous. So let's talk about, let's kind of talk about this, these discontinuities then. So then what they're gonna ask, so they don't ask it in this exercise, but you're gonna see it in there instead of in the homework, is they're gonna ask you, so they're gonna ask where are the discontinuities? So you tell them that x equals, my discontinuities. right? X equals -2 and x equals 2. By the way, really quick, notice that, so you see that in the graph. Let's say you didn't have this graph. And they asked you basically where the discontinuities in the graph or in the functions. So that's where we're going to get to. That's where we're sort of going to move to and go to today is we're going to start asking some of these questions. What's the limit discontinuities? But we're going to ask them without a graph, right? So it'll be your job then to look at the function as, look at the function in this equation form. And the key here, honestly, is to remember what the graphs of the type of function you're looking at looks like. But even if I didn't give you this picture, 1/x² minus 4 is a rational function. And going back to your college algebra, what do you remember about rational functions? So again, not the specific, what specific graphs looks like, but what these graphs look like in general. Good, so hopefully you remember that for rational functions, there are horizontal asymptotes, vertical asymptotes, you could have a hole in the graph. And those are all determined by what makes the top and bottom of that fraction equal to 0. So we'll kind of, if we need to, we'll kind of review that. But that's one of the key things that I hope you remember about those graphs. So I was talking a little bit last time about how calculus, all these problems are 25% new stuff, and then just a crap load of algebra and pre-calc, just assuming that you've kind of mastered those things. So one of the things to refresh your mind on, literally refresh your mind on, or even if you need to go back and find a college algebra book really quick and read it again, which I don't think you guys will need to, but one of those things to refresh your mind on is when we're dealing with rational functions, think of the pictures that you got when you're graphing rational functions. And you would always get sort of sometimes some U's here, sometimes some arcs here, but you would always have a vertical asymptote, maybe have a horizontal asymptote, you might have a hole in the graph. And those, the vertical asymptotes and holes in the graph were determined by what made the top and bottom of our fraction equal to 0. And that's specifically because it was a rational function. Now there were other functions that also had vertical asymptotes and maybe holes in the graph, or at least vertical asymptotes. What were some of those other functions that had vertical asymptotes? So going back to college algebra, you might remember that log functions have vertical asymptotes. And then even going back to some of our examples from the last lecture, you might remember that your cosecant, secant, and cotangent and tangent functions have vertical asymptotes. So it'll be your job to remember the kind of the qualities of these functions. So you're eventually, again, what we're going to go to with this, not only with today's lecture, but this class is you've got to cue those things in your mind really off of the equation. So once you see the type of equation, you should know in general what those graphs look like, because those those concepts and that knowledge from those graphs is really what's going to cue you off on how to work through the problem. So what I'm trying to get to is, even if we didn't have this picture, you would tell yourself, so this is a rational function. And what do I know about rational? I know if the bottom of the fraction is 0, whatever makes the bottom of the fraction 0 causes one of two things, either a vertical asymptote or a hole in the graph, an open circuit. And a hole in the graph, it actually happens when that, whatever that x value is, makes the top and the bottom 0. The vertical asymptote happens when just the bottom of the fraction is made equal 0. So that's the thing you need to remember, not for rational functions, and you'll see that come up a lot today, sort of as the class goes on. So I guess what I'm trying to get to is, even if you didn't have this graph, whatever makes the bottom of the fraction 0 in this case, since there's a 1 on top, it's going to give you a vertical asymptote. So hopefully you can see pretty easily from there that x squared minus 4, if you set that equal to 0, the only two possibilities there are -2 and 2. So the same thing we saw in the graph you could get by just setting the bottom fraction equal to 0 and solving. You get -2 and 2, those are your two discontinuities for the graph. Because it makes the bottom fraction 0, and you can't divide by 0. Let me actually, especially since we're gonna use it a lot today, but you guys are gonna be using it the rest of the class. Let me do a little, let me do a little summary over here. Let me just figure out how to title the summary, but let me do a little summary over here of a bit of what I was just talking about. Let's call this a summary of zeros. In my summary of zeros, what I'm gonna say is, in general, if you have 0 divided by a number, well, that just gives you 0. And again, if you didn't catch it from college algebra class, assuming your calculation is a fraction, if you do something like this, 0 divided by some solid number, something other than 0, that gives you 0. This actually tells you x-intercepts for that particular graph or function. Or we call them zeros or solutions. But if you have some solid number divided by 0, that doesn't exist. That's impossible. And this tells you a vertical asymptote. So if you run into a calculation for any function, not just for rational functions, not just for things that look like fractions naturally, I guess that's. Anytime you run into this calculation, some solid number, something other than 0 divided by 0, that is impossible. And that's what causes vertical asymptotes. One of the things that causes vertical asymptotes to show up in graphs. If you get a calculation that ends up as 0 divided by 0, that's actually not that it's impossible. The trick with this, or the kicker with this, is that every number is possible. The 0 times anything gives you 0. So they call this indeterminate. We can't limit it down to one right answer or a couple right answers. And this gives you, I guess the symbol they use for it, they call it an open circle, but I'm going to say hole in the graph, because I think that's a better description. So 0 divided by 0, if that calculation ever comes up in any of our work, that's indeterminate because everything's an answer. 0 times anything is 0. But more importantly, that tells you that you have a hole in the graph, which is one of the discontinuities that we've seen several times in our graphs so far. Okay, so sorry. Let's go back to again 33. They're going to say where are the discontinuities? You're going to say that x equals 2 and x equals negative 2. Then they're going to ask you, are these removable or non-removable discontinuities? So let's go back and look at kind of what we have. These are vertical asymptotes. And again, if you didn't have this, you could tell because they make the bottom of the fraction 0 and 1 divided by 0 is impossible. So that's a vertical asymptote. But we have the picture here, we see with the vertical asymptote. So again, the idea of a removable discontinuity is, could I replace what I have here at 2 with a point that then makes the graph continuous, where the value of the point would match the value of the limit. Yeah, the value of the point would match the value of the limit. And notice that it's impossible to do that. You can't, I could put a point somewhere here along this line, but whatever the y value is for that point, it wouldn't match the limits from the left and the right here. We said the limit from the left is positive infinity, the limit from the right is negative infinity. That doesn't, you're not going to get a point that matches those values, both those values. So that means there is no way to just stick a point there and smooth things over. So this is a non-removable discontinuity. Can't remove it, you're stuck with it. it's gonna mess things up. So then the same over here too, there's no point I could put somewhere here along this little invisible dotted line that is gonna stretch and cover the top and the bottom here. So this is also a non-removable discontinuity. So those are two good examples of non-movable discontinuities. Let's look at 34. So 34 is another rational function. First you have x squared minus 1 over x plus 1. And notice that, at least according to the graph, says that x value of -1, we have this little open circle. A hole in the graph. So basically this graph would be the straight line, would be one straight linear function except for that one point. Now, like I was just kind of summarizing for you guys, often, most of the time when you see a hole in the graph, it's because you have a calculation that end up with 0 over 0. So again, to jog you guys' memory on rational functions and what you learned in college algebra, the reason we're seeing this here is if you think about this, if we factor the top and the bottom here, if you factor the top, what would you end up getting? And so we're gonna be doing, so like I said, we're gonna be doing a ton of algebra in this class, 75% of every problem is algebra. I guarantee you're gonna be doing a ton of factoring. So we are back to every single problem. You're gonna be trying to churn out some factors and figure some things out with that. This x squared minus 1, if you factor that out, that's gonna be x plus 1 times x minus 1. And then on the bottom, we can't factor it any farther, so that's just x plus 1. Notice you get the same factor top and bottom. Notice the x value here is the exact x value that if you plug it in, so if you do -1 plus 1, that's going to be a 0, which will make the whole top 0. And -1 plus 1 also makes the bottom 0. So if you plug in -1 to this function, you end up with 0 divided by 0, which is why you get that hole in the graph. So if you end up with a solid number divided by 0, you get a vertical asymptote. If you end up with 0 divided by 0, you get a hole in the graph. So not only wanted to remind you of that, we'll have some problems where we're gonna have to actively start doing that little bit about the work. They're gonna ask you for the discontinuities here. And because of the picture, it's easy to identify, but even without the picture, you can do exactly what we just did. You factor the top and the bottom. You figure out what makes either the bottom 0 or both the top and bottom 0. And either way, you would figure out that x equals -1 is a discontinuity. Then they're gonna ask, is it removable or non-removable? Now notice in this case, like such as this graph is basically just a straight line with one single point missing. So if you put that point in there, so if I put the point -1, -2 in there, then this function suddenly would, first of all, it would be the functions would end up being continuous at that point, because by putting the point in there, so first of all, from the left, your limit is x approaches -1 from the left is -2. And your limit is x approaches -1 from the right is also -2. So this graph by itself, this function by itself, the limit had already existed and the limit was -2. But by putting that point in there now, the point does exist and the y value there is -2 and the limit and the point agree. And as long as they agree, then it's continuous at that point. So again, so what we're saying is this is a removable discontinuity. We could remove the discontinuity by just literally plugging that point in there. This is removable. So quite literally, what they're saying is we could redefine this function as a piecewise function where it's x squared minus 1 over x plus 1 for all the x, basically for everywhere except for that discontinuity. And then at the discontinuity, you just give it a value, say it equals -2 at x equals -1. So we literally are just like stapling the point in there. We're saying, here's my x, here's my y for that particular x value. And that would put the point in there, and that voila, you have a continuous function. So we can remove that discontinuity by just plugging the point in. That is a removable discontinuity. Especially because we will see functions like 35 later on in the course. Hmm. Wait a second. Okay, well, I think what I'll have you guys do is I would like you to do the same now with 35 and 36. But for both 35 and 36, I want you to identify where are the discontinuities. And then see if you can figure out whether these discontinuities are removable or non-removable. So I'll give you guys a little time to work on that. So pause on your side, I'll pause on my side. Go ahead and do the same thing that I've done for 33 and 34, do the same thing for 35 and 36. All right, let's get back into it, see what you guys got. All right, so where were there discontinuities? By the way, this is a good example of a function. So this function here, actually, give me a second. Visual is not incredibly clear. Oh, well, that's sort of a combination of a foreign being function. But either way, this is something that algebraically we don't have a clean way to evaluate this, or at least not that doesn't take that half page of paper. Anyways, so these are just two good examples of they're probably going to give you the picture of something like this. So sorry, but where were the discontinuities? Good. So you should see there's one discontinuity at -1. The limits from the left and the right don't match. So you don't even have a limit, which means can't be continuous. Also at x value of 0, also at x value of 1. There also is a discontinuity in x value of 2. So I want to talk about this point here, this open circle here. Notice that, so this is, in some sense, this is sort of the edge of the window. They're kind of considering this function from -2 all the way to 2. So at this rightmost point here, when you're talking about continuity, the limit needs to exist. That's one of our conditions, so the limit needs to exist. But if you're at the edge of your window, obviously you can't have a left and a right limit that agree with each other. So when you're at the edge of your window or your interval that you're looking at, for the limit to exist, you only need it to exist from whichever side, whichever direction you're sort of approaching that boundary, that edge. So I guess what I'm saying here is there is a limit here because from the left, it's approaching whatever that is, like 2.5, something like that. It's approaching about 2.5. So there is a limit here because from the left, it's approaching 2.5, and that is the edge of my window or my interval. So I can't even talk about anything from the right. And since I can't talk about anything from the right, you only need the left side. It would be the same over here if this was an open circle. So it would be the same at -2, that you would have a limit from the right, but not from the left. But that's okay because that still gives you a limit there. Good. So at the left-hand side and the right-hand side, the limits do exist. You just need the one side for that limit. But specifically at x equals 2, so at x equals -2, sorry, the limit exists there. So the function or the graph approaches -3 when you get to an x value of -2, and the point exists, and the point's y value is -3. So again, the limit exists, the point exists, they match. So it's continuous, the graph is continuous here, but it is not continuous here. The limit exists. Y, and the limit is about 2.5. But the point doesn't exist. Because the point doesn't exist, then I can't say that the point and the limit match each other. So that's also discontinuity. So my discontinuity is here. There's quite a few of them. Is what? X equals -1, x equals 0, x equals 1, and x equals 2. Good. And then the next question for each of these discontinuities, is it removable or non-removable? What did you all say there? I specifically not only chose this problem because it was the next in the next side set, but I specifically chose this problem. Second, I'll make sure. But I specifically chose this problem because these are open circles like our last example. But I didn't want you to assume because it's an open circle, it's removable discontinuity. So these are open circles like our last example. But notice that, for instance, at -1, I try to fill in that open circle with a point, I still have limits that don't match from the left hand and the right side. I still don't have a limit. So just filling in the point here doesn't solve the issue of you don't actually have a limit at -1, right? And there's no way to sort of smooth over that distance either. There's no, just like we're looking at with our vertical asymptotes, there's no point. If you try to put a point between the two there, it doesn't bridge the gap, right? You still don't have a limit there. So at -1, this is actually a non-removable discontinuity. Doesn't matter where you put an extra point there, the limit is never going to exist. It's never going to agree from the left and the right. So then that's the same for 0. Non-removable discontinuity. No matter where you put a point there, you're still not going to have a limit because the limit from the left and the limit from the right don't agree. And the same at 1 then. However, at 2, since we actually have the luxury of not having anything happening on the right side, that is a removable discontinuity. I can just put a point there, and then my limit, which is 2.5, agrees with the y value at that point, which is 2.5, and so it's continuous. So this is non-removable. 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 But this one is removable. And actually, I'm gonna pause it for a second. I think there's class in this room that I'm using, so let me see when their class starts. Okay, we're back. We're good. Nobody's coming into the classroom. Okay, good. So 3 non-removable discontinuities, but this one on the end is removed. So then on 36, what did y'all find there? Where were the discontinuities? Good. In this one, there's only one. So it would have been at x equals 1. The limit exists there, but the limit doesn't match the y value, so it can't be continuous. So for this one, 36. That's at x equals 1. Now the next question then is it a removable discount? Well, and it ends up that this one is a removable discontinuity because we could simply take this one point. So again, kind of like I showed you guys for one of those previous problems. But really, this point is here because at x equals 1, and they're just telling you the y value equals 2. So this is, again, a piecewise function. So you essentially have one part here that's defined by the top equation, top line. We have a second part here is defined by the bottom line, and then this little middle portion here is sort of defined by the middle line. So if we just redefine this middle line, we just say for x equals 1 that instead of 2, this is a 1, then voila, that point moves down there, it fills the space, and it's continuous. So this is a removable discontinuity. You want to mention where on 35 we couldn't have done that because if you found a way to basically make a piecewise function out of this and just sort of reassign these endpoints to match, the problem is you still if I move this point down here, that's great, but then I still have a gap between this point now and sort of the next bit of ink there, the next point to the right. So we couldn't have done that with this one just by moving points because you're still gonna have a gap with that next point. But here, I can just move that, that's like, sometimes it's like floating points. I just move it back where it should be and everything's great. So removable discontinuity. All right. A related issue that they're gonna ask you about in 2.5, I believe it's in 2.5, so we'll go there. So in general, they're gonna want you to be able to identify removable and identify discontinuities where they are, and then whether they're removable and non-removable. But a related issue, and going back to the summary of zeros that I told you about, was once you identify these discontinuities, if the discontinuity is caused by one of these zero conditions, one of these zero conditions, then I should be able to identify whether it's a vertical asymptote or a hole in the graph, which for a rational function means it's a removable discontinuity. So you're gonna get these questions where basically they're gonna ask you, is this discontinuity, where is the discontinuity, and is it a vertical asymptote or a removable discontinuity, a hole in the graph? Again, not all holes in the graph are removable discontinuities. Yeah, but we're just gonna look at some specific problems where it will work out. Anyways, so let's kind of look at those problems. Hmm. 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 Well, okay. We also should look at some. Hmm. All right, give me a second to find the problems I want to use for this. Alright, and we. Alright. So like I said, we're gonna look for both vertical asymptotes and removable discontinuities. In some of these functions here. So the first thing to notice is that these problems, but just these functions, the way they're given them, they're not giving you a picture. So let's try to look at a couple of let's start with 7. You wanna find they want you to find the vertical asymptotes of the function, and then I'll go farther and say go ahead and find removable discontinuities. They're there as well. So the first thing really is find the discontinuities, and then identify them as vertical asymptotes or removable discontinuities. So let's start with something like 17. So 17, first thing. So again, if you're not given the picture, you don't have the advantage like we've had on all the previous problems. The first thing is, again, like I was talking a little bit, I think it was in the last video, or maybe it was this video. Identify the type of function and then jog your memory on that. Go back to your college algebra, go back to your pre-cal, jog your memory on kind of what's going on with that function visually as far as a graph. So one of the secrets here is that in order to identify these things, we're going to do some algebra, but you still need to think about, you basically still need the picture, you still need the graph, or you at least need to think about the picture and the graph of that function and the different things that come up in that graph. So again, like I said, the first thing is what type of function is this? This is a rational function. It's polynomial divided by polynomial. That's a rational function. Always forever. So since it's a rational function, we're looking for discontinuities. Our two major discontinuities, so again, going back to your college algebra, thinking about those graphs, thinking about that time, the stuff that you learned about these rational functions. And then thinking about these problems we've been looking at. The discontinuities come up when you either have a hole in the graph or vertical asymptotes. Which a hole in the graph, like we saw, so like I said, at least with a rational function, if you think about holes in the graph with the rational functions, those are removable discontinuities. You can put a point in there and plug the hole, right? Plug a hole in the dam. So since this is a rational function, that tells me these are the two things I'm going to look for, and this tells me how to look for it. So again, that's one of the biggest things I want you to connect back to today is that if it's a rational function, you know that, and actually outside of rational functions, this is still true. So you just know in general, if I have a solid number divided by 0, that gives me a vertical asymptote. And if I have 0 divided by 0, that gives me a hole in the graph. This happens all the time with rational functions. So again, it's not that we're also gonna use this to figure these things out, and they're not rational functions, but if you're honed in on a rational function, definitely you're looking for these two cases. So we need to figure out what makes the top and the bottom of this fraction 0, because that's what distinguishes these two cases. A hole in the graph happens when you have 0 on an x value, an x that gives you 0 on the top and on the bottom at the same time. Vertical asymptote happens when that x value only gives you 0 on the bottom. It doesn't give you 0 on the top. So we need to figure out what makes the top and the bottom of this 0, and then I can identify these discontinuities pretty easily. That's your first thing, is to figure out what makes the top and the bottom of this fraction 0. And I actually want to give you guys a second to do that. Again, you guys have gone through college algebra, so I promise you already know how to do this. So if you're sitting there like, wait, hold on, what do I do? Or I need an example. I actually want to challenge you. You don't need an example. I want to get you guys to lean on what you already know and not always be looking for, a copy paste example that you've seen before. The thing is, you have seen an example before, but you're past the point of needing to see it immediately because you've already passed that class. You've already done college algebra, you passed it. I promise you, I want to get you to challenge yourself to just dig and figure out what makes the top and the bottom 0. You already know how to do that. And then we'll talk about what those discontinuities are from there. So I'm going to pause on my side, you pause on your side, go ahead and figure out what makes the top and bottom of this 0. All right, so let's see what you found. So the top is pretty easy. You set x squared equal to 0, and what that gives you is x equals 0. Bottom, you set that also equal to 0. Like we did on a previous problem, it'll help you there then to go ahead and do some factoring. So that's going to be x plus 2 times x minus 2 equals 0. And from there, you can easily see x equals 2 or x equals negative 2. So 2 and negative 2 make the bottommost fraction 0. 0 makes the top 0. So now let's look at what scenarios, what scenarios each of us gives us. So the 0 on the top actually would give us this first scenario, which is an x-intercept, because if you plug in 0 on the top, if you plug in 0, it makes the top 0, but it doesn't make the bottom 0. So that's not a discontinuity at all. That's actually a solution. That's nice. So that's not going to tell us anything as far as discontinuities go. So now let's look at the 2 and the negative 2. If I plug in 2 or negative 2, I know that makes the bottom 0. Does it make the top 0? No, not at all. You plug in a 2 to the top, you get 4. You plug in a negative 2 to the top, you also get 4. So in either case, you plug in a 2 or a negative 2, that gives you 4 divided by 0. And which one of these cases is that? Perfect, that's a vertical asymptote. So these both give us vertical asymptotes, actually. So our discontinuities. Our discontinuities here are x equals 2 and x equals negative 2. And in this case, these are both vertical asymptotes. And abbreviate that because I'm slow at writing. Anyways, so these are both vertical asymptotes, and you're good. So don't assume because they're asking for these things, don't assume that you're always going to get a vertical asymptote or you're always going to get a removable discontinuity. You may get one, you may get the other, you may get both. So really your approach here is, again, don't try to solve the problem in a special way to get a special answer. Just find your discontinuities first. And then take the concepts and identify what those are. In this case, they're both vertical asymptotes. Very good. Um, um, let's figure out. Um, I think these problems are designed to be vertical asymptotes type of thing. Yeah. Oh, actually, I'm sorry. These were the problems I was trying to get to. So what I'd like you guys to do then is I'll have you guys do the same thing. So identify the discontinuities and tell me whether they're a vertical asymptote or a removable discontinuity. But let's do that for, I don't know, let's do that for 34. Second. Yeah, my man. Yeah. Possibly. Same. Actually, what kind of like to do? Hmm. So I guess you say it. All right, so I think what we'll do is let me just have you guys do 33 really quick. We'll talk about some other types of functions. But I think for the sake of doing vertical outflow from we'll get discontinuity, let's do something like 33. Um, yeah, so you pause on your side, I'll pause on my side. Identify the discontinuities for me and whether they're vertical asymptote or removable discontinuity. All right, sweet. Let's look at it. Discontinuities here. And so again, what you would have had to do actually when they write this lower is work above it. And we're looking at 33. What you would have had to do is figure out what makes the top and the bottom of this fraction equal to 0. Set each equal to 0. X squared minus 1. So x plus 1 times x minus 1 equals 0, which means for the top there, you get x equals 1, x equals negative 1. For the bottom though, x plus 1 equals 0, that's basically already solved. That just gives you x equals negative. So now let's look at kind of our discontinuities, which these are discontinuities for us, and then what type it is. So 1 and negative 1 make the top 0. Notice that 1 doesn't make the bottom 0. So again, if I plug in a 1, it's going to give me 0 on the top, some number on the bottom, and that's actually an x-intercept. That's nice. But if I plug in a negative 1, it'll give me 0 on top, 0 on the bottom, and which type of discontinuity is that? Good. That's a hole in the graph, which is going to be in this case a removable discontinuity. So x equals negative 1 is our only discontinuity on this one. And it is actually a removable discontinuity. So when you see rational functions, that's definitely what you're looking for. Second. Let's go back up. Like I said, these are not the only situations where we see discontinuities. For rational functions, this tends to be our summary. But again, there, like I mentioned earlier at the beginning of the video, there are other types of functions that have vertical asymptotes just naturally as part of how that function graphs out. So I want to focus on vertical asymptotes for a minute. Again, to just jog our memory from college algebra. Um, so I think what I want to do. We're gonna have to split this lecture into a third part. Hmm. We're gonna talk through those examples. Well, sort of. Well, let's start with 28. So I want to jog our memories on that. Should I have vertical? And where do natural logs usually have vertical asymptotes? Think about that graph. Where is it usually? Good. So remember that a log or a natural log, the graph of this, so a thumbnail of this graph. So if it was just natural log of x, this graph would normally look like this. You would have a vertical asymptote right along the y-axis. So at x equals 0, we normally have a vertical asymptote. This +3, what is that doing to my graph? Good, it's moving the graph over to the left 3, actually. Sorry, so it's moving the graph to the left 3. So instead of my vertical asymptote being at x equals 0, where's my vertical asymptote going to be? Good, it's going to be at x equals -3. So for something like this, they ask you kind of where's the discontinuity, or actually here they're asking very specifically where's the vertical asymptote. There is no trick with zeros, unfortunately, to get anything. The only way you know that is you see natural log and you remember what that graph looks like. And you also remember your transformations of graphs. Again, you guys went and did in college algebra. So I look at this and I know normally my vertical asymptote is at x equals 0. +3 moves that to the left 3. So here I'm going to have a vertical asymptote. I'm going to have a vertical asymptote at x equals -3. And give me a second. So for these problems, do they give us an interval to work in or domain to work in? Yeah. There are other functions you come across in your math classes that have vertical asymptotes that again, you're not gonna, I guess we'll talk about, yeah, but they didn't have vertical asymptotes. And those were some of your trig functions. So for instance, cosecant, tangent, these all have vertical asymptotes. So again, it'll be your job to remember both from, remember from pre-calculus, along with using transformations of functions to figure out where those vertical asymptotes are going to be. So let's look at cosecants. Let's do one of these. Let's look at cosecants. So the first thing is, again, trying to remember back. I keep saying remember back, so hopefully you do remember back. And if you don't, that's fine. This is where, go ahead and get a graph going of this. Well, actually, I'm thinking, take the graphing calculator. Is it not? Yeah, for this class. Is it not allowed for this class? It should be. A graphing calculator should be allowed for this class. So yeah, whether it's that or Desmos or something like that on your, yeah, go ahead and get a graph going. Try to remind yourself. But either way, it also should be the graphs of these might be the appendix actually. But either way, take a second. So we won't even have to pause. I'll just kind of pace here. But where are the vertical asymptotes for cosecant? So normally the vertical asymptotes, but remember cosecant is 1 over sine. So when you start thinking about these trig functions that have vertical asymptotes, one thing to remember for pre-cal 2 is the reason we're getting vertical asymptotes is because of this. You're dividing a number by 0. So for instance, cosecant is 1 over sine. So when you get a vertical asymptote for cosecant, what's really happening is you need to identify where sine is 0. So I'm trying to write this out. So cosecant really 1 over sine x. So if I can figure out where sine x is 0, so let's say you don't remember where these are, you can actually recreate it. You don't have to memorize as much of this stuff as you think. Again, I'm a mathematician, so not just because I'm good at this, I'm smart. I'm a mathematician. I've published papers, research that's cited. I don't ever memorize this stuff because if you use the concepts and ideas, you can always recreate all these facts for yourself. You actually don't need to remember all this stuff. You need to remember the definitions, the concepts, the ideas, because that's with those you can always recreate all the ideas, all the facts that you need. So a good example of this is you don't remember cosecants from pre-calc class. That was a while ago, or you ate a big lunch and your mind is kind of foggy. Well, you do know that cosecant is 1 over sine. So if I can figure out what makes sine 0, then that has to be where my vertical asymptotes are. Because again, my vertical asymptotes are coming from this calculation here, a number divided by 0. So where is sine equal to 0? So think around the unit circle. Sine is equal to 0 at 0. Let's remember on the unit circle, sine is your y values. So at 0, y is 0. So at 0, sine is 0. And then over at pi, sine is 0. And then back at 2 pi, sine is 0. 3 pi, 4 pi. So every pi, sine is 0. Which means that every pi cosecant is going to be a vertical asymptote because you'll have 1 divided by 0. And that's a vertical asymptote. So my vertical asymptotes here should be, and we'll kind of we can make a little infinite list out of this. It should be something like negative, should be something like negative 2 pi, negative pi, every pi, 0, pi, 2 pi, etc. So you can write it this way. You guys have seen, previously your pre-cal and college algebra classes. You can write it this way. You could write it something like n pi, n being an integer, any integer. Kind of symbolic way of writing the same thing. As much as I'm a mathematician and we're supposed to love symbolic ways of doing things, I actually kind of prefer this because it both tells you every answer, but also kind of shows you every answer. This is hard to read. I feel like it doesn't show you much. It's correct. It doesn't show you much. I would write it some way like this. Now, the one thing you have to check here is these are the vertical asymptotes for cosecant of x. Notice that we have this pi being multiplied by x. So again, this is where I'm saying to remember your transformations of functions. I have a pi, I have multiplication on x value, which is a horizontal shrink. And a horizontal shrink for trig functions shrinks your x values. So it shrinks your period, which shrinks all these x values. So these would be where the vertical asymptotes are if this was just cosecant of x. But since it's cosecant of pi x, you're going to divide everything down by pi because that's what this pi is doing. It means it's going to shrink, it's going to squish the graph horizontally and shrink it by pi everywhere. So I'm going to divide all these by pi. And that will be where my vertical asymptotes actually are. That means my vertical asymptotes, sorry, we're still doing 29 there. My vertical asymptotes are actually going to be at x equals -2, -1, 0, 1, and 2, etc. That is still the answer. And again, that's something to, just stuff that you gotta remember, or pull back up, kind of cue back up, from pre-cal. Um, so you need to remember some log stuff from, what do you call it? From college algebra, you need to remember some sort of trig stuff from, pre-cal. And you're also gonna need to remember some of your, not just trig identities, but the way that we manipulated, expressions using our, what I call our, what I call trig functions and trig identities. You're gonna need to remember that from pre-cal as well. So for instance, let's look at something like 32 here. 32, again, they're gonna want vertical asymptotes for this. And they're giving you tangents divided by, tangent of theta divided by theta. Again, vertical asymptotes happen when the top is not zero and the bottom is zero. So notice that this is sort of a rational function and a trig function wrapped into one. Technically composed. So what we want to talk about here is, so in some sense, we sort of have double duty here. So even though the tangent is in the top of this fraction, we still need to identify where is this tangent going to give you a vertical asymptote. And then also, since this is, again, a trig function placed into a rational function, we still need to identify where the bottom of this fraction is zero. We kind of need to set both equal to zero and, I'm sorry, not even zero. We need to figure out what makes the top of vertical asymptote, or what makes the tangent of vertical asymptote, and what makes the bottom zero. So obviously for the bottom, that means theta equals zero is going to give us a vertical asymptote. If we do want to check, we need to plug zero into the top here. So what is tangent of zero? So I want you guys to actually think through that. So what is the tangent of zero? And the tangent of zero ends up equaling, oh, interesting. Okay. Just, well, this is a good example of a problem where kind of can't reduce it to a simple procedure. You just need to kind of figure out a lot of different things that are going on with it. So the interesting thing about this is if you plug in zero here, tangents, so tangent of zero is in fact zero. So zero also makes the top equal to zero. Yes, I'm so sorry, guys. Yeah. So this theta equals zero actually gives you zero over zero, which is not a vertical asymptote, but what is that? But that's a hole in the graph or a removable discontinuity. So here, zero is not going to give us a vertical asymptote. So theta equals zero is going to be a removable discontinuity. But where does what angles give you a vertical asymptote for tangent? Again, I won't pause the video, just take a second, I'll pace, go back and figure that out, see if you can find that. So hopefully you're again, looking back at some pre-cal book, or maybe you already have this in your mind, or you find some resource and what it should show you. So if you think about it, tangent is sine divided by cosine, so that was one of your identities from pre-cal. That actually helps us. So yeah, let me just kind of take this down here. That'll help us. So let's say you don't remember what the graph of tangent looks like, but you know the tangent is sine over cosine. So again, what I'm doing is I'm using some identity from my pre-cal class to remind myself that even if I don't know the picture of this, tangent is sine over cosine, which now makes it a fraction. Now means I can apply this, figure out my vertical asymptote. So this is going to have a vertical asymptote every time cosine is equal to 0. And for what values does cosine equal 0? So again, think about your unit circle. Go around with unit circle. The first place where cosine is 0 is pi over 2. Then it's 3 pi over 2, and then it kind of keeps wheeling from there. 5 pi over 2, 7 pi over 2. You can go back in the negative direction. So the places where this is 0 is theta equals, so again, maybe negative 3 pi over 2, negative pi over 2, pi over 2, 3 pi over 2, etc. And it keeps going from there. So that means that's where my vertical asymptotes are. Theta. So that's removable discontinuity, and then my vertical asymptotes are at theta equals, and we'll just repeat this list. Negative 3 pi over 2, negative pi over 2, pi over 2, and 3 pi over 2. Okay, now would be my vertical asymptote. So I try to highlight these, say, you're gonna get, these are in that, like I was saying at the beginning, I think of actually the last video, or somewhere in the last video, that calculus is about looking at these same functions you've seen before in, what I call it, college algebra and pre-cal, but then doing some more operations, figuring out some different things, doing something different. So they're going to ask you to find vertical asymptotes, removal discontinuities for any functions that you've seen so far and any combinations of those functions. So it really calls for you. You have to go back and take your knowledge, take the concepts that you have, take the mastery that you have of what you learned before with those functions, and that becomes your tools for figuring out this information. So I'm going to split this into a third video because we still really need to get to, if they don't give you a picture, so we need to go back and look at how do we find the limits when you don't have a picture. We've done a lot here with discontinuities and what types of discontinuities there are, etc., which is something you need to be able to identify. So for this video, we'll cap it at that. We'll have a third video for this week that will then be, let's just go find the limits of these functions without having a graph. All right. So again, when you get to this homework and they're asking this, just the one thing to know here is, the problems that I gave you are, some of the functions and some of the combinations, but they're not every one of them because I couldn't. It would take me hours to write every single combination, and that's not even the point. Again, the point is, you know enough from these previous classes that not only, I'm not going to show you every combination, but I shouldn't have to show you every combination. Use the things you know, use the concepts you know about all these functions. And what I'm saying is actually you don't need to see every combination. I guarantee you can figure it out. You can figure out where the vertical asymptotes are, where the discontinuities are, purely from what you already know. For any combination that they give you. So So you guys are good for these type of questions on the homework. I will end this video and I'll see you for I'll see you next for the third one. See you then.